Good morning to you, my dear students. I want to welcome you to this lesson this Saturday morning. And to all the viewers and students that follow the BBS teaching program, I encourage you to continue following our program. Today morning, I want to begin by congratulating our colleague, our Ugandan athletics hero, Cheptegei, for winning the 5,000 meters race. And I want to use that incident to motivate and encourage my students, my followers, and the people attending this program, that Cheptegei won simply because he has been practicing. He has been practicing and he knew what he exactly wanted. I think he still remains, I'm not very sure, but he still remains with a record to break the veteran athlete Bekele, who set up a record that I think is yet to be broken. Why am I using Cheptegei? I want to encourage my dear learners that if you do not practice, definitely you find challenges. Learning is like farming. I will summarize in a few minutes and we go to our lesson. Learning is like farming. You must prepare the gardens very well. If you are to do farming, you must look for the quality seeds. And you must, if it requires fertilizing, you must fertilize the soils. When it reaches time for weeding the crops, you must weed. When it reaches time for spraying the crops like it is these days, you must spray. I will not mention about the GMOs. Probably if there is any official in the Ministry of Agriculture following, they should know that there is a problem with the GMOs. I'm told those seeds do not actually allow the produced seeds to be planted and germinate again. So students out there, I want to encourage you to continue weeding. Continue, if there is need to prune. But continue watering your gardens, continue reading your books, continue doing whatever you expected to do. I have already said that God gives free food to the birds of the air. For those that have been my students, you know. And for those that are my students during this COVID time, let me let you know. God gives free food to the birds of the air. And I always say, is there any bird that you have seen and they say it owns a garden anywhere? And of course the answer would be no. But don't they eat? They do eat. Who gives them food? God. But where do they find the food? God gives birds of the air free food, but he doesn't throw that food in their nests. They must go to look for that food. So my dear students, I want to encourage you that you must have the personal ability, the motivation, the self-drive to look for your food. Your food is in books, your food is in teachers, your food is in programs like this one, your food is on the internet. It is there all over. Learning is like firing bricks. If you want your bricks to get well burnt, you must ensure that the fire is kept constant. For bricks, you may not need all dry wood, but for learning or for cooking food, you may need dry wood, and make sure the fire is constantly there. I want to encourage my learners following this program that you need to ensure that you are firing your academic work consistently. That is when you will be able to get what we all desire for you, we all desire for this country and for the world. I want to, with those few words, welcome you to my lesson. A quick review. Last time we were looking at applications of total internal reflection, and we were able to, among others, look at the total reflecting prisms. We looked at the total reflecting prisms. We identified very many other applications. I want to quickly look at the erecting prisms, and then thereafter we shall have a few basic examples and we shall proceed as the lesson flows. Please enjoy the lesson. We look at the erecting prisms. One, we must use a 90-45 prism. In this case, I am going to begin by illustrating using this simple diagram. It is a 90-45 prism, and what is its purpose? Its purpose is to actually give an erect image. That's why it is called erecting. It gives an erect image of an inverted object upon total internal reflection. And we shall see that it is able to actually reflect light through 180 degrees. So if we have an object over here that is inverted, a ray from the bottom of that object incident, what shows that this ray is incident is the arrow. It is from the object. And another ray from over there, incident, will be reflected. If it is 90-45, what I want us to note is that this is 45 degrees, and even over here is 45 degrees. Now this light, because of that of what I'm going to just explain now, as we discussed last time, we said if light is incident normally, it is not refracted. This is air, this is glass, as I shared, and this is air again. Where we have air, we could have a liquid. But this angle is 90, therefore this is also 45. Now this light ray is going to be refracted here. I am using a free hand, but these are supposed to be straight lines. Even this is going to be refracted over there. Now, if we look at the geometry of angles, right over here, if I introduced a normal, as I showed you last lesson, it would imply that if this is 90, 45, 45, this is the whole of this is 90, it means this is 45 degrees. My emphasis here is we got the critical angle of glass as 41.8, which we approximately said is 42. And that means that if the critical angle of glass is 42 and this angle is 45, it means that the angle of incidence is actually greater than the critical angle. And this is the condition we looked at to give us total internal reflection. So this light is totally internally reflected, and the same thing happens here. Because this will still be 90, this is already 45, even here will be 45. So this angle even here will be 45, and 45, and so on. And this is also 45, this is also 45, and so on. So this light is going to be reflected internally again here, totally internally reflected again, and we'll actually give an upright image at this point of the original inverted object. The image that we get here, this is an erect image. An erect image. This is an inverted object. And that is the major reason why we are saying that this prism is an erecting prism. It uses the principle of total internal reflection to give an erect image or an upright final image of an object. So we can summarily say that light at this point is reflected through 90 degrees. Even at these other points, it is further reflected through another 90 degrees, and therefore the total reflection is through 180 degrees. We can say that light is reflected. Light is reflected through 180 degrees, and an erect image obtained from an original inverted object as shown in our diagram. As shown in our diagram. We shall use this concept. I'm saying that light is reflected through 180 degrees and an erect image obtained from an original inverted object and an erect image obtained from an original inverted object is obtained. You can say is obtained from an original inverted object as shown using the prism binocular. We can look at a question here that we shall use to apply that principle. We can look at this question. We have a diagram. Let me make it a little bigger. The ray of light is over there. And these angles are given. A ray of light, as the question goes, is incident on a face of a glass block of refractive index 1.52. The ray emerges normally from face BD. This is face BD, and they are telling us it is expected to emerge normally from that face after total internal refraction. And they are asking us to find the value of the angle I. They have given us the refractive index as 1.52. So our task is to first complete this diagram and then use the principle of refraction to find the value of I. Since this is already given as 90 degrees, this light is going to be refracted to hit that face. And the angle of refraction here, we are going to find it. If it is refracted, it is incident here. If we do the mathematics, we shall come back. It is incident there, and they are saying it emerges normally through this face. So it means it is refracted here to give us a 90 degrees angle here. But since this is a quadrilateral, these four angles are supposed to be added up to give us 360 degrees. So this angle over here is supposed to be 90 plus 150 plus 60, taken away from 360. 90 plus 60 is 150. 150 plus 150 is 300. And therefore, this angle becomes 60 degrees. If this angle becomes 60 degrees, it implies that this angle is 30 degrees. Since this is 90, it automatically means this becomes 30 degrees because it is a glancing angle. If we consider that there is total internal reflection here. And of course, we are not interested in the values here, but this would be 60 and this would be 60. Now, if we work backwards, given that this is 30 and this is 90, we obtain this again as 60 degrees, and therefore obtain that as 30 degrees, and then we proceed. After clearly fixing the angle geometry, remember we need I. We shall use n sine I is a constant. Remember, this light is from air, and therefore we have been given a refractive index of glass. The glass block has that. It means n air, the sine of I which we want, is equal to our n glass, the sine of I, but this I here is, this R is going to be considered as I. That is 30 degrees. When we substitute right over there, we shall be able to get our NA is 1. Our N glass has been given 1.52. My following students, I expect you have your calculators there. Our sine I will therefore be equal to 1.52 times a half. The sine of 30 is a half. And when we compute using our calculator, we shall get our I as the arc sine of, I think it gives around 0.76, which gives us our I as 49 point approximately 5 degrees. We get our I as 49 point approximately 5 degrees. It is important to those following, take note. Yes, this diagram is given as a sketch, but the candidate is expected to complete the diagram using the information given in the statement. They are telling you that the ray emerges normally on this face, and therefore it is important that after drawing a correct diagram, you work backwards to fit in the angles, and then after fitting in the angles, you eventually end up getting this value, and knowing that I, light rays are reversible, this I can be I, this can be I. So the R can be considered as an I if you reverse light, therefore That's why we feed this in as an angle of incidence on that number. I did talk about the other methods. As applications of total internal reflection. Allow me at this moment to ask officially the students following this program to do research. In my teaching, I usually advise and encourage students to do some bit of research, and that usually makes or enables students to find life at the university very easy, because they already know how to go into textbooks and do some research. So I'll ask you to research about these two applications. The use of fiber optics or optic fiber, but I'll mention briefly about it. Students should also research about the occurrence of mirages. But just for purposes of knowledge and information, I want to say that fiber optic, recently you must have seen lots of excavations on the roadsides. The Ministry of ICT is trying to extend the fiber optic cable underground. They dig those roadsides and put fiber optic cables. The fiber optic cables use the principle of total internal reflection by ensuring that the signals, as we are talking on your phones, the signals that are transmitting whatever messages you are passing on move with less interference if they are actually moving underground. There is less interference than one would get if they are moving in space, as you may be aware. So the fiber optic cable, you will discover that is a cable that has glass mixed or protected with rubber. And this glass uses the principle, as you discover, you'll find that it uses the principle of total internal reflection, but it has a layer that protects the signal, that when light enters, this light will be continuously reflected totally, internally, until it eventually comes out. So I am asking the learners following this program to do a little more research on how the fiber optic cable operates. But I am basically illustrating that. The other thing I want them to do research about is the occurrence of mirages. Mirages are what we normally see on a very hot day, usually on tarmac roads. For those who may not be active students but are following this program, you tend to see an occurrence of a situation of a pool of water a few meters in front of you, only to appear and there is no water. Candidates are usually asked to explain the occurrence of mirages on a cold day. It does not only happen on a hot day, but you need to know how total internal reflection affects light that is coming from the sun and hits that surface on the ground and creates a situation that is seen to be a mirage. That will be research work. I want us to proceed and look at how we can measure refractive index. Measurement of refractive index. I want us to discuss how we can measure refractive index of a liquid. By the air cell method. Measurement of refractive index of a liquid by the air cell method. A refractive index of a liquid can be measured using very many methods. When I was talking about mirrors, I did not mention, but allow me to emphasize, I did not mention that you can measure refractive index using a concave mirror and a plane mirror, and the refractive index would be for a liquid. But students following this program should be able to read and understand that when a mirror, a concave mirror is placed on a plane mirror with its reflecting surface facing upwards, you must emphasize that, then an object placed above the mirror, probably clipped on a retort stand, can be moved up and down until when that object coincides with its image. We usually call it the no parallax method. When that object coincides with the image, you note and record that distance from the mirror to the coinciding point. Then a small liquid is then introduced on the surface of the concave mirror, and the new position of coincidence is looked out for. Once we get that new position, then you should be able to finalize that experiment by getting the expression for the refractive index. For the air cell method, we shall discover. I will use a simple diagram to illustrate. Students should note that the type of light we use here should be monochromatic light. Mono means one color, and an air cell is basically a combination of two glass slides. Two glass slides. I'm going to assume these are glass slides. That's one. This is the second one. And these glass slides are put in a cross section where we have the liquid in there. The liquid is in there. The glass slides assume or will have some air captured in between. So we have an observer. If light is coming from a source of light, we shall say we have our monochromatic source of light here. So this light is incident up to the first slide of our air cell. And we will have a scale. We'll have a scale which I can put over there. We'll have some kind of scale that is attached there. And of course, there is a device that may not be fully shown on this diagram. But an air cell method ideally is a container. You have a container, and you'll find some books. We'll put that container there, and outside here there is a scale, which I'm emphasizing. This would be a collection of two glass slides. I am giving an extrapolated image that should be able to indicate that this is our liquid, whose refractive index we need, and this can be called the air cell. We shall use two plates. The combination of this is what we call the air cell. And this space in between our slides is air. So light is going to pass through. In between here, we put an extrapolated light ray, but it will come through to the observer's eye. It will come through the observer's eye. That is diagram 1. If I am to re-emphasize this diagram, I can still draw a small cross-section here and say that this is my air cell. I'm going to use 3 different diagrams. This is my air cell. Now I am not going to put the enclosure. I have the liquid this side, and I have the liquid that side. I will still put my light ray. It's the same diagram. I'm now not going to label this. And I'll have my observer over there. We usually put the eye to illustrate the observer's position because we can only tell that that is the eye. Now here, this space is occupied by air. And as I said, this is glass and this is glass. This clearly emphasizes what I'm calling an air cell. It is a correction of, or a combination of two glass slides put together, but in the process of putting them together, you capture some air in between, and then the air cell is put in a container which has a liquid whose refractive index we need to find. What happens in our explanation? What happens in our explanation? I will bring it in writing shortly, but I will proceed to draw the last diagram, and then I will explain fully what happens. Now, what happens is that the air cell is going to be rotated in the liquid. It is going to, because it's an application of total internal reflection, it is going to be rotated until the light is cut off from this observer here. And it is rotated in a known sense or in a known direction. Now, if it is rotated until you obtain a situation where light is cut off from the observer, it implies that total internal reflection has occurred. It implies that total internal reflection has occurred. And when total internal reflection occurs, just prior to the occurrence of total internal reflection, it means light that is incident, this light here, is grazing the interface of that first glass. And it also means that it grazes when the angle of incidence after rotating is now equivalent to the critical angle as we saw earlier. So, after rotation that I have talked about, after rotation, I expect that the glass slide is now in a rotated kind of position. So I will consider this as my new diagram after rotation. This is a method that is very common, and some learners actually fail to get this concept correct simply because it is not well explained. Now, after rotation, we are saying that if light is incident over here, if this is the angle of incidence, let me call it theta, after rotation, this light is going to be refracted over there, and it is going to graze the interface. It is going to graze the interface here. Remember, this is air, and you know that the other one is glass. If this is air, if I'm to put a normal here, this angle is 90 degrees. This is air. We know the refractive index of air is that. And this is glass. The refractive index of glass is Ng. Now, that diagram is what we obtain with this side having a liquid all over and this side having a liquid all over. If we actually include this again in that kind of cross-section, it means you have the liquid all over. It could clearly be seen if these slides were drawn beyond so that the liquid does not go there. But I want us to emphasize our discussion here that when the air cell is rotated in one direction, you rotate it until when light is cut off, measure the angle of rotation from the scale, of course, and then for accuracy, we usually must rotate it again in the opposite direction until light is cut off again. The same angle will actually be obtained. After rotating it in one direction, say clockwise, When light is cut off from the observer, rotate it in another trial, but now in the opposite direction. And then we shall be able to get our value of the angle. Now, from this diagram, if I use the expression that n sine I is constant, n sine I is constant, I will have my n liquid. This is the liquid, the sine of I. The I in the liquid is theta. Right over here, our I is theta, will be equal to the n. Now, this light is in glass, so it will be equal to the n glass here, the sine of the angle. If I let this angle be, remember here, the angle that is responsible for making this 90 is the critical angle. This angle here is the critical angle. And if we consider the geometry of angles, this angle is equal to that. So this should be the critical angle. And if I proceed to come even here, I'll say it will be the same as n air times the sine of 90 degrees, because 90 will also become an angle of incidence if we reverse light. When we use that reasoning, considering this and that, since we are interested in refractive index of the liquid, NL, the sine of theta, can be considered to be equal to 1 times 1. I am using N air as 1, and the sine of 90 degrees is also 1. This implies that my N liquid, which you are looking for, is the same as that. However, we have not reached the very end of this explanation. To reach the very end, you'll discover that since I told you that the air cell is rotated in one direction first and then rotated in the opposite direction, again, the angle of rotation, which is this that we are calling theta. If I called it theta, that angle of rotation, that we are interested in half that angle, because light is cut off when you rotate it in one direction and you change the direction. So since I called that theta, if we let this angle be alpha, it implies that there are two values here, that theta plus theta is equal to, if there is an angle in here, is equal to alpha. And therefore theta will be equal to alpha over 2. So if we substitute for theta, our NL will actually finally be equal to the sine of a half of alpha, which will eventually give us the last expression that we are supposed to use. That if the total angle of rotation in one direction to the other is alpha, then we can get alpha in terms of theta in terms of alpha and be able to obtain our refractive index. The explanation that is missing is rotating the air cell in one direction until light is cut off, then rotating the air cell in another direction until light is cut off, and then obtaining the whole total angle, which we are calling alpha. But that alpha will be 2 times the angle of incidence that I called theta. And therefore, if theta is expressed in terms of alpha, we can therefore obtain our expression as NL for the liquid as 1 out of the sine of alpha over 2, because it is alpha that has been measured on the scale. This method of determining refractive index by the air cell method, refractive index of the liquid by the air cell method, is a very common question, and learners need basically to master these diagrams. The first diagram is you use a monochromatic source of light to provide one color light, and you are saying light will be passing through up to the observer's eye when the air cell is parallel to each other. When the air cell is rotated slowly until light is cut off, the diagram will come to this one. And that means it is cut off when you have the total internal reflection situation there. And we use that application to be able to derive that expression. As we move towards the end of our lesson, I want to emphasize that, like I usually say, it is not how much you cover in a particular lesson that matters, but how much you cover and understand. I want us to look at this question, and it should be able to bring us to the end of our discussion today. We have a triangle here, and we have light that is incident normally and refracted through a prism. Incident normally, we are all aware, much as this may not look like a 90 degrees, that we said when light passes normally, it implies that the angle at which it enters is actually 90 degrees. Even if we don't complete the discussion of this number, I am sure the learners should be able to try out. When the prism in question is rotated, in the clockwise direction, when the prism is rotated in the clockwise direction through an angle beta at a point, the refracted ray grazes, does not emerge. That means it grazes, does not emerge into air. Then they want us to show that if the refracted ray does not emerge in air, show that the sine of C times the sine of the angle which I have called beta should be equal to the sine of C minus beta. Show that that would hold where, of course, where C is the critical angle. To summarize this solution, this is our question. They are telling us to rotate that prism through an angle theta. If we rotate it, it implies that we can say finally, after rotation, we could get a diagram of this nature. If it is rotated through an angle theta, it means the angle similar to that diagram, the angle of incidence of the light ray is now beta. The angle is now beta, and that means if light does not emerge, it is refracted and grazes this face. So it is exactly that diagram over there. That if it grazes, this angle is C, and that angle is the same as this. The refractive index of this glass is given as N, and they are telling you to show that that actually happens. Now, if this angle here is let to be, they are telling us when a prism is rotated in the clockwise direction through an angle beta, at a point the refracted ray does not emerge. So if we let this angle be theta, then it implies that this angle would be this is the beta, and therefore this angle we can take it to be any angle, say alpha. If we take it to be any angle, it implies that this is R, but which is C. So at any point, say point B, at point B, I want to emphasize that if we apply n sine I is a constant, we will have that this angle, but that I'm calling alpha, if you look at this as C, this is 90 minus C. And therefore, if we are interested in finding C, we shall find that if this angle is R, we want to find that angle. Considering this as a triangle BCA, we will need to find alpha, that alpha plus R will actually be equal to C if you work out, and therefore your R will be equal to C minus alpha, where this is R. Using this reasoning, you will use your n sine I. NA, the sine of beta, should be equal to your n, the sine of R. But if this is R, you can do the geometry. You'll get that the sine of beta would be equal to the refractive index n times the sine of C minus alpha. C minus alpha. You will have to bring in the other angle in the picture using refractive index. Using refractive index, you'll have to bring in the other angle. That since n is equal to 1 out of sine C for at critical angle, then we can substitute for that and get that the sine beta of beta is equal to 1 out of the sine of C times the sine of C minus alpha, and finally sine of beta times the sine of C would become the sine of C minus alpha minus, this should be beta, sine of C minus beta as required. If you rearrange, you'll be able to get that expression as, sorry, this should be beta. You may wonder where is the alpha coming from. This should be beta, the sine of C minus beta. So you should be eventually able to find out that. I want to stop here. Learners, there is some bit of information I've not shown here as to how you get the R, but you can do that as research. I want to wish you the best and encourage you to do the given assignment. Research about prisms. Next time we meet, we shall be talking about prisms. I also want to, of course, remind you to continue following all the work on my YouTube channel. I wish you a good weekend. God bless you. Gachari Mabaga.